Hi, Year 9. In this question, we're told that the digits of a two-digit number sum to 10, and if the digits swap places, the number is 36 more than the original number. And the question we're asked is, what is the original number? And specifically, we're asked, can we show an algebraic solution? And the reason for that extra prompt is because if you take some time to think carefully about this question, you can realize that the answer, the original number, can be determined without using any algebra at all. So what I might do is, before I jump into showing you how we can do this algebraically, what I'll do is I'll give you an opportunity to pause the video and have a think to see if you could use early primary school knowledge to work out the answer to this question. Okay, hopefully you've had a chance to think about that. Now, the key to the non-algebraic approach for this question is to hone in on the requirement that the two digits must sum to 10, because there's only a limited number of digits that meet that requirement. We could have 1 plus 9 equaling 10, 2 plus 8 equals 10, 3 plus 7 equals 10, 4 plus 6 equals 10, and 5 plus 5 equals 10. So really there's only 5 combinations of digits that meet the first requirement. So we can really take a brute force approach to this by then testing for each of these combinations of digits, do they meet the second requirement, which is where if the digits swap places, the number becomes 36 more than the original number. So it is possible using simple addition to really take a brute force approach to this question and get to the answer. So let's do that now, and then I'll work through the algebraic solution. So if I start with 1 plus 9, the number that we would get when I put 1 and 9 together is 19. And then if I swap the digits, I'd get 91. And then the question is, does that satisfy the second requirement? So is 19 plus 36, is that equal to 91? And it's not, it's equal to 55. So we say that is not equal to 91. So the first set of digits can't be the answer. Now we can repeat this thinking with 2 and 8. So the two-digit number we would get would be first be 28, that's the original number. If we swap the digits, we get 82. And the question is 28 plus 36 equal to 82? And it's not, it would be equal to 64. So again, 2 and 8 can't be the digits. Moving on, if we look at 3 and 7, putting those together we would get 37. And then if I swap the digits, I get 73. And the question is 37 plus 36 equal to 73? And yes, it is. So that means we have our original number. The original number is 37. Now again, if this was a primary school question, you could stop here and that would be your answer. You wouldn't even need to worry about looking at 4 and 6 or 5 and 5 because we already have the answer. And we got there pretty quickly without any algebra. But the point of this question is to see whether we can show an algebraic solution. Knowing that the answer is 37, the answer isn't really the main idea here. What's more important is the working out. That's often the case with algebra. The answer isn't the big deal. It's more about can you show the working out, because then you could use similar techniques for harder problems where taking a brute force approach may not be practical. So what I'll do, just like before, I'll give you an opportunity to pause the video and see if you can think of a way to get to this answer of 37 by using algebra. All right, hopefully you were able to come up with an approach that would get you this answer of 37 using algebra. if you didn't work it out, the key is to use simultaneous equations. And whenever you have a worded problem like this and you need to use simultaneous equations, step one is always to define your unknowns. So with simultaneous equations, there's going to be two. So what I'm going to say is let's let the two digits be x and y. They're typically the two letters we use for unknowns. We could, in theory, use any letter, but x and y will work fine. Now what we need to do is come up with equations that represent the requirements in the question. And the first requirement is that the sum of the two digits, or x plus y, needs to equal 10. That's the first requirement. So I can label this equation as equation 1, and that will come in handy later. Now, the second requirement is that if the digits swap places, the number will be 36 more than the original number. So what that really means is that if my original number is xy, then when I swap the digits, I get yx as being my number. That is going to be equal to xy plus 36. That's the next piece of information. Now, that's not in its most helpful form right now, but what we can do is we can expand the numbers. So again, this is really using primary school knowledge, but we need to remember all the way back in primary school that when I have a two-digit number, the first digit represents the tens column and the second digit represents the ones column. So really, if I wanted to expand these numbers, instead of writing yx, I could write yx as 10y plus x, because that is really fundamentally how I can break up that number. And I can do the same thing with xy. That's really 10x plus y plus 36. That becomes the right-hand side. And now I can clean this up a little bit. I could subtract x from both sides, and I'd get 10y is equal to 9x plus y plus 36. And then I could subtract y from both sides, and I get 9y equals 9x plus 36. And then I could divide both sides by 9. So I'd get y is equal to x plus 4, because 36 divided by 9 is 4. And that I could call equation number 2. Now, I've got two equations, and if I want to solve these simultaneous equations, I've got an option. I could either use substitution or elimination. In this case, given I've got one of the unknowns all by itself on the left-hand side, substitution's a pretty natural option. So what I will do is I will sub equation 2 into equation 1. And so what that will look like, if I take equation 1, wherever I see a y in equation 1, I'm going to take the right-hand side of equation 2 and substitute that in, because y is x plus 4. So I'll end up with x plus, and instead of writing y, I'll write x plus 4. That is equal to 10. So that means 2x plus 4 is equal to 10. If I subtract 4 from both sides, I will get 2x equals 6. And if I divide both sides by 2, I will get x equals 3. And that's looking good, because we know that the first digit needs to be 3. Now, to solve for the second digit, we can substitute x equals 3 into equation 2. And that way we'll get our value for y. So y will be equal to 3 plus 4, which equals 7. And therefore we can conclude that the original number is 37. And again, we knew that because we had already worked that out using our non-algebraic approach, but this is what it would look like using algebra. So hopefully that's all made sense and you're able to work out both approaches. And it's a really good example of how there is often more than one way to answer a question, but even though you could have used very simple addition to get to this answer, it is also important to know how you could have used algebra so that, again, as I mentioned before, if you do encounter more complicated questions where perhaps there isn't a simple alternative, then you can use the algebraic technique and you'll know what to do. All right, tick boom.